Okay, so this is the lecture 24. I think that this will be the last lecture for transient simulation, and for remaining two lectures we will consider the small signal analysis. So today we have not many lecture content, but actually its implementation is quite involved to someone, so please be careful. So first of all, we will talk about the example related with mixed mode simulation. So please note that although mixed mode simulation itself provide us the general capability to consider any kind of circuitry in our simulation, but unfortunately in our current implementation we just consider this simplified version. Yes, we have a device and it can have multiple terminals, and we can introduce a resistor to each terminal. So then that is terminated by a voltage source. So there is a voltage source, another voltage source, and another voltage source, and there is also a resistor, another resistor. That is the implementation we can do right now with a simple rule like external voltage minus I times R will be used as internal voltage, and this internal voltage will be used the actual voltage directly applied to the device. So let me just discuss this topic once again later. So this is an example, so please try to follow my example with your own implementation. Consider a symmetry and abrupt p-n junction. So its doping density is for both sides 10 to the 17 per cubic centimeter. We have used this one quite many times, and assume that electron mobility is a constant and hole mobility is also a constant. In reality, so electron mobility and hole mobility, these quantities should be considered as varying quantity depending on electric field or other quantities. However, right now we will just use two constant values for mobilities. So this is understood, and the area is 1 square micrometer. So from the top view we have 1 micro and 1 micro. A square is formed, and we wanted to attach 1 kilo ohm to this PN junction. So the resistor is just 1 kilo ohm. Then now I wanted to increase the voltage up to 10 volt. So we have already discussed this one in our previous lecture, but let me just repeat again. If we increase our input voltage up to 10 volt, then anyhow this D1 and R1 should divide this 10 volt, the total 10 volt, and it takes some part and the other is assigned to R1. However, if D1 takes this 10 volt, then if we consider exponential increase of our D1 current, then if we have 10 volt all applied to D1 current will be really humongous. However, in that case, we have if 10 volt is applied, then we will have 0 volt, and this 0 volt means that there is no resistor current. Certainly, the diode current and resistor current should be perfectly balanced, so that is not the situation we wanted to have. Then, why don't we have just 9 volt and 1 volt case? Well, so somebody can say that maybe there is some possibility. However, please note that since D1 current is rapidly increasing by D1 voltage, so actually the current level covered by this covered by this uh, diode current is quite wide. However, that is narrowly placed only about around 0.7 volt or 0.8 volt depending on the doping density of our PN junction. So simply speaking, if we have 9 volts directly applied to diode and 1 volt, then this 1 volt will generate small current, and this 9 volt will generate two large current. What we can expect is the drain, oh sorry about that, not drain but diode voltage is around 0.7 or 0.8 volt for turning on the diode, and a little additional voltage that is enough for working with this D1 diode, and all of other quantities or other voltage, the remaining voltage is assigned to this R1, and R1 will drive a certain current. So maybe to someone not familiar with this concept, then it sounds a little bit strange, but please understand this D1 is so steep. Whether you have 10 times larger current or 10 times smaller current for D1, that does not change the voltage across this D1. Anyhow, if we have some measurable D1 current, then the range of D1 voltage is more or less given. So now all other voltage is applied to R1. That is the qualitative understanding on this problem. So now you are looking at the numerical result in the right figure. So here we have input voltage as a x-axis, and output voltage is used as a y-axis. So this is the one. So this is nothing but the applied voltage to a resistor. So since D1 voltage is more or less just below 1 volt, so all of the remaining voltage will be applied to this one. So simply speaking, input voltage, output voltage. So here this is line over 8, and this is a vertical line over 8. So that is actually this red curve corresponding to our input voltage, and you know that this blue curve is corresponding to the output voltage. So simply speaking, your output voltage just follow input voltage, but not exactly. There is a certain offset, and this offset value is approximately about 1 volt. So you can just copy your input voltage to output node with some cost for operating this rectifier circuit. Of course, this is all related with the bias condition larger or higher than this voltage level, and if we go to this way, then actually this is nothing but just 0. So now no voltage, output voltage is generated, and no non-zero output voltage is generated. So this is numerical calculation. So it seems to be quite easy, but my caution about your own implementation now follows. So if you wanted to really solve this seemingly simple problem, then you must consider both of the voltage, output voltage, and cathode current as your unknown variables. So please try to implement it. So do you remember our previous discussion? So in our previous discussion, I told you that our unknown variable vector contains the internal physical quantities, electrostatic potential, and carrier densities. Actually, that was all for our previous implementation, but now we have to add two more quantities like so cathode current and output voltage as an unknown variable. Then what will happen? So let me just okay, so maybe this is a good place to write down something. So let me just consider our matrix. So here we have a large vector corresponding to internal variables, and previously we had a Jacobian matrix corresponding to these unknown variables. However, now we must consider the cathode current as an unknown variable and output voltage as another output unknown variable. So then now say that we have some numbers of size. So this is quite large in general. It can be the order of 1,000 or 1/10 of 1,000. So we have quite a large matrix already built, but what is the additional size originated from the introduction of these two variables? Now we have two more variables. Then what will be the size of our overall Jacobian matrix? Now you can easily understand by adding these two numbers. So our Jacobian matrix should be enlarged in this way by two entries and by two entries. So that will be the total size of our Jacobian matrix. So do you have any question? Then please interrupt me. So please interrupt me. So then how can we consider these two lines? Here we have two lines, one line and one other line, and this the first line first new first line is corresponding to our cathode. Now in this case we can say that I cathode is given by integrating our Jn value and Jp value for our, so in this case let's say that this is cathode surface, and yes, this expression is required for our new line, and previously it was just a number, you can calculate it. However, now it should be considered as what? Considered as another unknown variable. So now you can have something like this. You have I cathode plus this integration should be 0. That is your residue for this line. And what you have to do is taking the partial derivative of this residue with respect to your cathode current. What will happen to this partial integration? This partial integration will give you just number positive 1 because cathode current is already inside your list of unknown variables. So you will have just 1. That will be assigned to number 1. Wow. Is it all? No, certainly we have to consider other parts. So this residue has also another ones like this one. What is it? This is just the integration of your current densities over certain area quite close to the cathode surface. So what we can expect is by taking this residue with respect to, for example, phi 0, phi 1, n 0, n 1, p 0, and p1, each of these partial derivation will give you non-zero values because this integration is highly localized around the cathode contact, and cathode contact in our case is corresponding to x naught. So the quantities corresponding to the node, cathode node, and the nearest neighbor, they are required. So when you have just a new Jacobian matrix, then we can visualize newly added component as this way. Here we have the one corresponding to the cathode current, and this line just to specify our cathode current is a function of internal physical quantities. That is the one we need for this second last line. Then how about the last line? The last line is about V out. So V out is just internal voltage. So this is internal voltage. So that is given by our applied voltage minus times current and resistor. So please think about our specific example. In this specific example, we are now talking about this one. And what is the applied voltage at this node? The external node, that is exactly 0 volt. So now we can say that this applied voltage can be regarded as just 0. And how about this I and R? In this case, I should be cathode current and R should be also cathode resistance. So in this case, in our example, specific example, it was set as 1 kilo ohm. So now our residue becomes V out plus I cathode times R cathode equal to 0. That is our residue. Then when we take the partial derivative of this residue function with respect to, for example, our V out, then what will happen? So this one will give you just number 1. Simply number 1. So we have once again diagonal component 1. However, there is another one. Not only this V out, but also I cathode is another unknown variable, and that will give you the Jacobian entry corresponding to here. Here you will have a R cathode. So that is not that easy, not that difficult. And you know, all of these entries are just identically 0 because it is nothing related with our internal physical quantities. Well, So are you happy with this implementation? So when you have a look at it, this matrix is corresponding to the internal and internal interaction. However, this second or these two last lines is corresponding to we are talking about IV characteristics, external one, and that is affected by these internal physical quantities. Internal physical quantities sounds great, but please note that there is one thing missing. What is missing? This is this part here, this block, just to describe what happens if we slightly change our internal physical quantities. Then what will happen to our IV characteristics? That is shown here. It simply means that if you change physical quantities inside, but that is not directly related to your output voltage. And another one is if you change internal quantity, then it is directly corresponding to change of your cathode current. That is described. Oh, good, sounds great, but still there is one thing missing. What is missing here? The missing part is not in this block, but you can find that this is the missing block of our constellation. When we change our cathode current or output voltage, then is there any impact on our internal physical quantity? That is my question. And since out voltage is just cathode voltage, we must consider that when out voltage is changed, then our physical quantity, the electrostatic potential attached to this cathode contact should be affected. So if you don't understand, then please review this recorded lecture once again. So I wanted to say, or directly ask me the question. So there will be certain law like this. In this law, maybe we will say that the electrostatic potential at the very first node is given as the equilibrium electrostatic potential plus cathode applied cathode voltage. That was the implementation in your simple single device implementation. So you load in that way x naught minus phi eq minus 3 cathode, that should be 0, and this is your residue function. But at that time your V cathode was not treated as an unknown variable. That was just a given number, actually 0. But now you realize that this V cathode is what? That is actually our out voltage. So when we take the partial derivative of this residue function with respect to V out, then it will give number -1 originated from this term. So simply speaking, you must have here -1 for your Jacobian matrix. So are you with me? Without this one, if you just omit this term, then even though when you change your output voltage, but your internal physical calculation does not consider the effect of this boundary value change, so your convergence will be degraded significantly. So please note that when we expand our original system into this little bit enlarged system by adding two more entries, two more unknown variables, then we must consider both of this lower part and upper part uh, carefully. So please try to do so. Yes.
저 아이캐스토드에서는 디스플레이스먼트 등 고려되지 않나요?
Right now, we are now talking about the steady state solution. So in this mixed mode simulation example, this is not taken from our transient result. So that's the reason why I just wrote in this way, and of course you are right. So if we consider the general case, then of course we have to say in this way. You are perfectly right in this sense, so we must write down in this way. But right now, I just told you the steady state solution, so that was omitted. In general, this form is the correct form. Any other question? So it seems to be quite a little bit complicated, but please try to do step-by-step manner. If you consider just two additional equations and its implementation in this line is not that much difficult. However, don't forget this one. It is easy to just forget this one, because you say that okay, these lines are already good enough, so usually you don't care about this part. But please note that in order to make the fully coupled system between our internal quantities and IV characteristics, you must consider this kind of reactions. Okay, so we can, in some sense, we can visualize it in that way. The matrix, here we have one matrix and another matrix, and the matrix component inside here is the relation between the quantities inside the matrix, and also this diagonal block is corresponding to interaction between the quantities corresponding to this block. But the off diagonal block here, you can have off diagonal block and off diagonal block. This block just describe the impact of unknown variables in this box to the diagonal box. Also, this box can be considered as impact of the unknown variables in this box into the solutions in this diagonal box. So those kind of diagonal components should be considered carefully. So if you just omit one interaction, then well, eventually you will get some degraded convergence behavior. So now let's visit my own experience with the example code convergence behavior. So when the Jacobian entries for the terminal currents are neglected, so in this example, what I did is, so I just implemented the good implementation, so correct implementation. After that, intentionally, I just omitted this part. Okay, now current is not exactly correctly calculated inside the Jacobian matrix. Then what will happen? The answer is quite easy. I use quite a small voltage spacing 0.05 spacing, so this is fine enough. However, we cannot get the converged solution at 0.8 volt. What is the value of 0.8 volt? At 0.8 volt, now the diode current becomes so large. So since diode current D1 becomes so large, so the voltage drop from this V out to ground, which is given by what? If this is D1 times R cathode, that will generate this V out. Of course, this cathode resistance is a fixed number, does not change. However, if we change the bias voltage, then we can easily increase this diode current and our output voltage will be affected by changing of our internal quantities. However, if we neglect this kind of interaction, then we cannot get the solution, converged solution. It is simply diverse. Why? Because in its Jacobian matrix, we have a long Jacobian matrix and it predicts a long way to update our solution variable. Then why we don't have a convergence problem? For example, 0.5 volt or 0.3 volt. In that case, since our diode current is so small, even though we have a long value, however, the voltage drop across these two node points is really negligible. So it is virtually just grounded. So since V out is well captured as virtually ground, so this one does not degrade your convergence behavior. Only when we have a non-negligible value for our diode current, then that affects our convergence behavior. That is one thing, and we can think about another one. So now let's come back, and I want to recover my previous correct implementation. Okay, now we have once again perfect implementation. After that, I just delete this part. Now our internal physical quantities does not understand that when V out is changed, their internal boundary condition should be changed. However, now my long Jacobian matrix does not understand that one. Then what will happen? Once again, simply speaking, I just neglect the one like this. Okay, so sorry about that. Sorry about that. I just in this experience, I just use a different one. So in this case, terminal. Oh, so I think that I made mistakes. So this is not this way. So sorry about that. So when I just neglected this one, that still we have a problem at 0.8 volt. Why it is important? So it is once again, this is related to the bias condition that we have a non-negligible current value to affect our output voltage. So although my second item seems to be a little bit not very clear, but my point is in order to have converged result for this system, you must be careful to consider both of these off-diagonal blocks. Then only when you implement it in a correct way, then you can get a well-converged solution. otherwise something strange will happen. So it's how can I say, debugging will take quite annoying. So even from my own experience, uh, it is quite annoying because there can be so many chances to make the sign confusion. So sometimes is it plus or is it minus, and or there is many additional components. But as I told you in this slide, this is the one you follow. Please consider all of these off diagonal blocks and this new diagonal block carefully. Then eventually you will get quite well converging solution. So in order to get the potential difference smaller than 10 to the maximum potential difference smaller than 10 to the minus 5, it takes just 5 or 6 Newton iteration in average sense. So if it takes, for example, 50, 60 times Newton iterations to get a solution, then certainly something is obviously wrong. So please note that even when we consider this much more complicated system than a single diode or single PN junction, when you implement it correctly, its convergence behavior is not that bad. So please, so the convergence behavior simply becomes a good indication of your implementation. If it converges quite fast, then it indicates that, oh, your implementation is good. And if it takes long simulation or many iterations, then certainly it means that internally something is wrong. So it is very important to consider both of them. Both means that current and voltage accurately in the Jacobian matrix. So my suggestion is, before moving to the transient device simulation, please try the DC one first. Even this DC implementation will not be quite easy. So even from my experience, so that is not that easy. So please try to simulate this simulation. Any question? So if you have any question, then please let me know. I the reason why I'm just repeating this kind of question to you is I wanted to give you sufficient time to follow the lecture progress. So now I hope that all of you have developed the DD device simulation single device, but adding this simple capability is not that easy. So I allow you to catch up the lecture progress. So now I assume that you now implement this mixed mode capability with some certain restriction. And now let's go to the transient device simulation. We will use the same rectifier circuit. So previous circuit is called as rectifier, and now the input voltage increased up to 2 volt. So we have already increased up to 10 volt. So what is the difference? But in this case, now we have introduced lamping rate. So previously it was just a collection of DC simulations. However, although the voltage is changed from 0 volt to 2 volt, but we can now think the lamping rate. So we can slowly increase the voltage, or we can rapidly increase the voltage. In this first slide for our example, I just adopted a lamping rate which is extremely low. So 1 volt per second. Within 1 volt, it just increased 1 volt. So since I just increased our input voltage up to 2 volt, it means that actually this lamping takes just 2 seconds. Quite a long time. Within this quite a long time, the voltage is slowly increased. Then what happens to our output node value? So as expected, so when its value is low, then no output voltage. However, beyond a certain level, now the additional applied voltage is all consumed by our resistor. That is shown here. This is quite much expected, and this is actually exactly same with our DC simulation, because this is extremely slow. So simply speaking, our delta t in this lower part to calculate round over round t, this delta t is too large, so this operation gives you almost negligible value. So that is almost identical to your DC simulation result. Then what will be the next slide? Please try to estimate or predict what will happen. So now, instead of this extremely slow one, we will try to extremely fast transition. Then if we introduce extremely fast transition, then this delta t will be increased several orders of magnitude. Then it is no longer negligible, and it contributes quite a lot to our device simulation. Okay, so for your reference, I just wanted to open our previous file. So okay. So in this transient simulation, what we have to do is consider this additional time derivative terms, and its implementation can be done in this way. Please note that once again, this one is the past electron density, and it is not included in our unknown variables. So it is just regarded as a constant value. Okay, then when you implement it, then you can have this kind of behavior. Now we have much faster lamping, and now the lamping rate is, instead of 1 volt per second, but now 1 volt per picosecond. Oh, picosecond is 10 to the minus 12 second. So I just increased the lamping rate by 12 orders of magnitude. So then now please have a look at this. Is once again our output voltage, and this is input voltage. If everything is just normal, then maybe you remember or you expect this kind of behavior. However, at the initially, here you can see that your output value just follows your input value. This is really strange, but please note that why our resistor voltage does not follow the input voltage in this line, in this range. It was only because here we have a diode, and in this case, for example, if we apply 0.5 volt to this point and ground it, then this diode takes all of 0.5 volt. Why? Because it tried to it is almost, in this case, it is almost okay. So so I'm confused. So please note that if everything is just normal, then our output voltage should follow this way. However, in this case, we have quite much different behavior. So I just wanted to give you your own exercise. Please implement this simulator and please check your internal quantities. Why this kind of strange behavior is happening. So simply speaking, although the analysis is your role, however, simply speaking, since our uh, diode is too quickly biased, so our PN junction cannot respond properly. In order to have the proper response of our PN junction, our electrons and holes should be redistributed corresponding to the applied bias. However, even our electrons and hole takes some time to rearrange. So since our damping rate is so high, our electrons and holes cannot follow such a fast signal. So that's the reason why our response is highly deviated from the usual expected one. Okay. So now instead of this just linear lamping, in this slide we are now considering the sinusoidal signal. So actually the sinusoidal signal is used for practical case, and when you apply the sinusoidal and when we have a relatively low frequency 1 megahertz, then what happens is shown here. Once again, this is input voltage and this is your output voltage. So if you have 2 volt and with a certain offset voltage, now you have just copied your input voltage. So here you can see from here to there, you can see that you have input and output. Input is copied to the output. Okay, good. However, we have also another phase where our input voltage is now negative. In the case of our negative voltage, then our PN junction becomes highly resistive, and all of voltage applied negative voltage is consumed by our PN junction. So nothing is left for our resistor. So that's the reason why we have just 0 in this part. So simply speaking, when we have a certain 1 megahertz signal, then what happens? Now we have the signal like this. So importance between this and that is like this. Please try to calculate the average of this blue line within a period. What is the average? You know that since this is sine, pure sine, so its average is just 0.04. So I want to say that in this case, input voltage has 0.0 DC component and 2 volt amplitude for 100 megahertz signal. So that was the input we have applied to our rectifier system. Then let's have a look at the output voltage. Then here, what is the average? Is it still 0? No. In this case, 0 and 0, and in this part we have a positive number. So simply speaking, when we take the average over a single period, what we get is a positive. We have no idea what it is exactly, but we can say that now we can generate a positive DC voltage. Then question is, how about 1 megahertz signal? Do we have a 1 megahertz signal? Yes, we have it, although it is not purely sinusoidal, but there will be certain signal like this, and its period is always 1 megahertz. So now you can say that we will have non-zero 100 megahertz signal, and also we can have 200 megahertz signal, 300 megahertz signal, blah blah blah. Here blah 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 means that the integer multiple of our fundamental frequency 100 megahertz. We can find this harmonic component, non-zero harmonic component. So are you all with me? So it simply means that this way, here we have our rectifier circuit. This is a rectifier circuit, and what we inserted here, let's say that here we have certain channel, frequency-wise channel. Let's say that this is DC channel, and this is 1 megahertz channel, 200 megahertz channel, 300 and 400 and whatever. In this case, in terms of our input voltage, which one is activated? So we have no DC component applied and no 200 megahertz applied, 300, 400 megahertz, nothing. We have just inserted purely sinusoidal 100 megahertz signal. We have applied a pure tone. Then please try to draw your output. In this case, do you have this tone? Yes, you have it. Do you have a 1 megahertz tone? Yes, you have it. Also, you have many non-vanishing components for your frequency components. So simply speaking, if we just neglect this unused channel for your input, then it can be visualized in this way. Wow, in this rectifier circuit, you just apply a pure tone, this pure tone, and this pure tone generate the DC component and harmonic component. So wow, you can establish this kind of mapping condition. Why do you have this kind of mapping between different frequencies? You just applied 1 megahertz, so you expect is just getting 100 megahertz. If you give the garbage, then garbage in and garbage out. That is a normal situation. But now you give 1 megahertz, 100 megahertz, but it generated so many unexpected harmonic components including DC. The main reason, the reason why we have this kind of a frequency conversion is so simple. Simply, this rectifier has non-linearity. If we have just a linear circuit, then 100 megahertz signal will be converted into 100 megahertz signal only when you have non-linearity. Then you can map your single frequency into the harmonics of that frequency. That is the one we have to understand. So, but anyway, that is the contents of our usual microelectronics course. But since some of you are not familiar with this concept, so I just repeat this concept again. Well, this is well understood for low frequency case, but if we go to the high frequency case, then our first period looks like this. Once again, this is input voltage and this is now output voltage. Wow, why do we have this kind of behavior? The expected behavior was something like this, but it is no longer looks like that way. For example, in this case, our reverse biased PN junction should take all the bias voltage, however it does not consume it, so it is not working as a rectifier at all in this case. But I wanted to say that this is the very first period, so whether it is really working or not, in order to test your result, then you have to perform multiple periods, because this response contains the large signal steady state response, at the same time also transient response. So you must wait for a while, several periods, then this very initial response will be diminished. After that, you just the real response of your system. So unfortunately, for that reason, transient simulation sometimes requires nearly several periods to get the final solution. So that is the main motivation to find out another way to calculate the response. So in general, transient simulation is a universal tool to observe the transient behavior or time-dependent behavior of your system. It just follow the physical law of your system and wait a long time, then eventually you will get the ultimate response of this system. That is quite good and straightforward. However, in order to get, you have to spend several periods, and sometimes it is quite painful to simulate long time. So sometimes people wanted to just the final result directly instead of having the initial transient behavior. This one is not actually interested to us. Then our question is, what happens if we just insert? So for example, if we just 100 gigahertz signal, then what is the amplitude of our DC term, and what is the amplitude of our 100 gigahertz term, and what is the amplitude of 200 gigahertz term? These kind of amplitude information and of course phase information, they are important to the engineers. Sometimes they don't want to much care about the for short time response in this case, because that can be quickly diminished in realistic application. So instead of taking the full transient operation, sometimes we wanted to develop a way to quickly calculate only the stabilized solution response. So I think that the full discussion on this capability will be beyond our scope in this semester because we have only 2 remaining lecture hours. However, what we can do is, instead of considering full relation between 100 GHz to DC, all over this calculation, but what I can cover in this semester within 2 lecture hours is just this 100 gigahertz to 100 gigahertz relationship. This can be covered in our lecture, 2 remaining lectures. So that is related with our so-called small signal analysis, or sometimes people call it as AC analysis, and it is closely related with the sensitivity analysis. Also, it is quite much related with variability analysis. All over. So I think that if you are coming from other department, then you cannot understand right now the importance of these issues. However, to engineers, actually, this kind of thing is quite important for example, RF engineer. To them, this is their job. And sensitivity analysis or variability analysis, that is related with reliability of our transistors. That is critically important for foundry service or any kind of integrated circuit. So all of these analysis methods are closely related to a single method. What is the single method? The method to calculate response of your system under a small perturbation. So in the next lecture, we will start to discuss about the perturbation. So of course, perturbation analysis is not only used in this electrical engineering, but it is also used in physics or any kinds of science and technology disciplines are using the perturbation. But in the remaining 2 lectures, I will give you our version or TCAD version of perturbation analysis to give you practical help to understand these important topics. Okay, today's lecture is over now, and if you have any question, then please feel free give me any question. Okay, so you don't have any official homework now because you are much involved with doing your own term project, so I will allow your time, but please try to follow our lecture progress because this topic is so important. So not only restricted to, how can I say, our own lecture contents, but it can be found some analogies in your own applications. So please try to find out the way to catch up our lecture progress. Okay, if you don't have any question, I wanted to wrap up today's lecture. Thank you.